A roller coaster car is traveling at a speed of 20 meters per second when it passes through point B. At that point, it enters a concave down circular sectional track that has a radius of curvature of 60 meters. After it reaches point B, the car's speed increases at a rate of 4 meters per second squared. Determine A, the time it takes the car to reach point D, and part B, determine the x and y components of the overall acceleration of the car when it reaches point D. So the first part of this problem, well, first let's just sort of set the stage. We're given that the radius of curvature is 60 meters. So that means that this radius vector here is 60 meters. We're told that when the car reaches point B, it's traveling at a speed of 20 meters per second. So that means the velocity vector at point B is going to be perpendicular to the path. So it's going to look something like this. And that speed at that point is 20 meters per second. At point B, it then enters this concave down section. And after B, the speed increases at a rate of 4 meters per second squared. So the acceleration, mainly the transverse acceleration, is 4 meters per second squared. Now for part A, we want to find the time it takes the car to reach point D. The way I attacked this problem is I first found the total distance traveled as the car goes from B to D. So B to D is a section of the circle. The opening angle is 50 degrees, so we have a theta of 50 degrees. And this angle is equal to, in radians, it's going to be 5 pi over 18 radians. So therefore, if I call the distance traveled, or the path length, let's call that S, the path length traveled by the roller coaster as it goes from B to D, S, will be the radius, which is 60 meters, times that 5 pi over 18. And so the path length that I find is 52.36 meters. So that's the distance that the roller coaster has to travel in going from B to D. We can use our basic kinematic equations to find the time it takes for the roller coaster to travel that distance. So the distance is equal to v0t plus 1/2 a t squared. So we have 52.36 equals the initial velocity, the velocity at point B, that's 20 meters per second, times the time plus 1/2 times the acceleration, which is 4 meters per second squared, times t squared. If I bring the 52.36 over to that time, I have 0 equals 2t squared plus 20t minus 52.36. This is a quadratic formula. I can solve it as such. I get that the time t equals negative b, which is negative 20, plus or minus the square root of b squared, 20 squared, minus 4 times a times c. Now c is negative, so there's a 52.36. I make this positive, and then I do all of this divided by 2 times a. That's 2 times a is just 2 times 2, which is 4. So I continue working this out. I get that t equals negative 20 plus or minus, when I take the square root, I get 28.62 all over 4. So I get that t equals, I'm going to get one that's positive and one that's negative. I want to keep the answer that's positive. So I get t equals 8.62 over 4. So this is 2.15 seconds. That's the time it takes for the roller coaster to travel along that path of the curve. So that is the answer to part A. And part B is a little bit more involved. Part B wants us to find the x and y components of the overall acceleration of the car when it reaches point D. Okay. So the best set of coordinates used to describe this motion initially, the most natural set, would be the transverse and normal components. So we write the acceleration vector as v dot times the unit vector e sub t plus v squared over rho unit vector e sub n. Now v dot is just the acceleration that was given to us in this problem. So v dot, we know, is just 4 meters per second squared. V dot is a constant. It's the same at point B and at point D. In order to find the v squared over rho, we need the velocity at point D. So the velocity at D we can find by using that the velocity equals the initial velocity plus the acceleration times time. So in our case, that initial velocity was 20 meters per second, plus the acceleration is 4 times the time that we found above, the 2.15 seconds. So the velocity at point D, I find it to be 28.6 meters per second. So I can take that velocity and compute v squared divided by the radius of curvature rho. So that's 28.6 squared over the 60 meters. And when I work this out, I get 13.63. And that's an acceleration. It's going to have units of meters per second squared. So the acceleration vector, written using the transverse and normal coordinates, is 4 times the unit vector e sub t plus 13.63 e sub n. So that's the acceleration at point D. What does this look like? Let me first start by sketching the track. So this here is point B. It's a little exaggerated, that's point D. Here is that segment of the circle. This is 50 degrees. And now let me draw those vectors. So E sub t is going to be tangent to the curve at D. It's going to look like that. And that has a magnitude of 4. And the normal acceleration vector will point towards the radius, just like I've drawn it. And that's going to have a magnitude of 13.63. So that is the acceleration vector, except it's represented in using basis vectors of the transverse and normal components. What the question is asking us to find are the components in the x and y direction. So in other words, what we essentially want to find, and I'm just sketching this, is an x vector. Let me draw it in a different color here. I'll use white again. We want some x vector, it might look something like this, and some y vector, it might look something like this, that in the end gives us the exact same vector, but it's just written in a different basis. Okay, so we need to find what the magnitude of this is and what the magnitude of this is. So the way we do that is, let me draw the transverse and normal components of the acceleration again. Let me first start by drawing this horizontal line. This point here is point D. At point D, I have my a sub t vector, has magnitude of 4, and the angle that this makes with respect to the horizontal is going to be 50 degrees. And then I have my normal vector, which points like this. This has a magnitude of 13.63, and this makes an angle of 40 degrees with respect to the horizontal. For each of these vectors, I want to decompose it into the x and y component. So for example, let me start with the transverse, which is the one that has a magnitude of 4. This will have a x component that is 4 times the cosine of 50, and it's going to have a vertical component, which is pointing down, which is 4 times the sine of 50. Let me go to the normal vector, which has a magnitude of 13.63. It will have an x component, which looks like that, which is 13.63 times the cosine of 40. And it will have a vertical component that will be pointing down that looks like this. And that will have a magnitude of 13.63 times the sine of 40. So we can now express the x component of the acceleration. We'll call that a sub x. Will then be 4 cosine of 50, it's positive is going to the right, minus 13.63 cosine of 40. The y component, well, let me just work that math out. If I work out that math, I get negative 7.87. And the y component of the acceleration, they're both down, so they're both going to be negative. I have negative 4 sine of 50 minus 3.63 sine of 40. And when I work this out, I get negative 11.83. So my acceleration vector will be negative 7.87 I hat, the unit vector in the x direction, minus 11.83 j hat, that is the unit vector in the y direction.